Okay, in the previous videos, we introduced the concept of systems. We did the qualitative definition as well as the mathematical representation. Now, henceforth, we'll be studying some of the properties of the systems. And the first important property of a system is the linearity property, whether a system is linear or non-linear. So, a system which is linear is a one. So let me just write it there. A system is said to be linear if it follows a superposition principle. Fine. So a system is said to be linear if it follows the principle of superposition. And this principle of superposition, it basically has two criterias, right? And the first one is that what is known as additivity, right? It simply means if I have a system wherein my output is y1t, this is the typical definition of the mathematical representation of a system. So I have a signal, I have an input x1t, the system, I feed this signal to a system, there is some transformation, and that is mathematically represented as this. Similarly, if I have to the same system, if I apply this signal x2t, it gives some another response, say y2t. Okay. Now the principle, this criteria of additivity states that if you want to satisfy this property of additivity, then if the same system is fed an input signal which is the sum of these two inputs x1 and x2, your output should be a linear sum of the individual outputs. This is the additivity property, which is the first criteria of superposition. I have a system, I give two separate inputs x1t and x2t. It gives me two separate outputs y1t, y2t. Now if the system satisfies the property of additivity, it means if I give a combination of these two inputs x1t plus x2t, my output should actually be the sum of the individual outputs. Okay? This is the additivity, and this is the first part of superposition. Second part is second criteria of superposition principle is what's known as homogeneity. Yeah, in some textbooks they call it scaling property. And as per this property, if I have a system given by this expression, I have input x1t and system performs some transformation which is represented by this, then if I scale my input, scaling in the sense amplitude scaling, I multiply it by some constant factor a, then if the system is homogeneous, if it follows the principle of homogeneity, then that scaling factor should appear in the output as well, right? That is additivity and homogeneity. And if your system, it follows both these properties, additivity as well as homogeneity, we say that it is a linear system in the sense that it follows the principle of superposition. So if I am to write a complete definition of a linear system, so it may be something like this, that the linear system, it basically should include additivity as well as homogeneity. So I may write as that the linear system is a one, yeah, just yeah, is a one whose response to a weighted sum of inputs, input signals, since we are expressing systems in terms of input and output signals, is equal to the same weighted sum of output signals, right? Each output signal being associated with a particular input, right? That acts on the system. So what I'm trying to say is that if I have a system, let me show it graphically. This is a system. It has a system property h. I'm giving an input x1t. It's giving me output y1t, right? Then again, I have the same system represented by the system property h. I'm giving the input x2t. It gives me y2t, right? Then same system, if I give it a weighted combination of these inputs, that is to say, I'm giving, say, a x1t plus b x2t as an input. So this is the first part of a definition, whose response to a weighted sum of input signals. Fine. So this is what I mean by weighted sum of input signals. Now I'm giving this kind of an input, and if it turns out कि जो output यहाँ पे है, that's y of t, if it is equivalent to the same weighted sum of outputs, which is the second part of the definition, is equal to the same weighted sum of output signals, each output signal being associated with a particular input. If you see, y1t is associated with x1t and y2t is associated with x2t. So if your system has this kind of a behavior, we say that it follows a property of linearity and it is a linear system. Fine. So this is just to make you explain, where I have taken only two inputs, x1t and x2t, which are weighted using the weights a and b. But in general, we can have a general analysis here. Instead of only having two inputs, I can have n number of inputs. So I will quickly do a general kind of a mathematical analysis. So let's say, let h represents, let's start with the continuous time system, then we can generalize it for the discrete time case also. So let h represent a continuous time system, and I am applying an input x of t, which is a linear combination of inputs a xit. So you can say it is basically something like this: a1 x1t plus a2 x2t, right up to last one, which will be an xn t. Fine. So in the previous case, just to put forward the concept, I had taken only two signals, x1t and x2t. Here I am generalizing, right? So these, so let me just put it here, jo x1t, x2t, right up to xnt, they basically denote a set of input signals, right? And जो weights associated है a1 a2 right up to a subscript n, they denote the corresponding weights, right? Now when this input x of t is applied to my system, I can write it that y of t is equal to the transformation h on this input signal x of t. Right? Yeah, I can write as transformation, since x of t is itself is a sum, is this made up of these weighted components. So I can say it is I running from 1 to n ai xi t. Right? So let's call this equation 1. Let's call this equation 2. Right? Now if the system is linear, then from the superposition principle, so if the system is linear, then it should satisfy the principle of superposition, which means that this system should have an output y of t, which should be the same linear combination of individual outputs. So I can write that thing as this, right? Which means it should be something like this: a1 y1t plus a2 y2t right up to an ynt, right? Where these yits, that is this, it is the output of this system to input xit, right? That is, yit is basically the output of the system acting on the xit in isolation. Fine, जो individual components है x12 x2t x3t, इनका जो individual है output है in response है, that is basically yi of t. So if I substitute this thing here, what I will get is that y of t will be summation I running from 1 to n a of I h xi t. Fine. So this is a kind of a general expression for the output of what you call a linear system. Generally speaking, I'm not restricting to only two signal components x12 to and x2t. It's a general thing. Fine. Fine. To summarize, if you have to check for linearity of a particular system, you have to ensure it follows the property of additivity and homogeneity. So just we'll take a quick example. We'll be doing a separate numerical session that will be in real time with a live demo session. But here, just to put forward the concept, I have a discrete time system which is represented as y of n is equivalent to n into x of n. Fine. And I have to check on linearity, whether this system is linear or not. Fine. Okay, so the system is something like this. You have a system with the system property h. You're applying an input sample x of n, and as an output it is producing an output y of n, wherein the sample value, that is x of n, is being multiplied by the argument n itself. And I have to check whether this is a linear system or not. So which basically means I have to define an input. So let us define input x of n as a linear combination of two inputs, a1 x1 n, a2 x2 n. Fine. Further, let me assume कि जो individual response है, that is something like this, that is y of n, y1 of n is the individual response of this system to the signal x1 n, which will be n into x1 n, and y2n is the response of this system to the signal x2n taken separately, taken in isolation, which will be equivalent to this. Right? So it is something like this. I am taking the systems individually. I am giving the input x1n, it is giving me an output y1n, which is equivalent to n into x1n. Then again I am taking the system in isolation. This time round I am feeding it with x2n, and it is giving me y2n, which is equivalent to n into x2n. Now I have to find the response of this system to the combined signal defined by this. Okay, so if I take this signal, the response will be y of n transformation of this signal a1 x1n plus a2 x2n. That is the weighted linear combination of these individual inputs x1n and x2n. Right? So the response of the system is such that it isolates this n and multiplies it with the input as a whole. So in response to this input, it will give you this output. So if I solve for the brackets here, it will be something like a1 dot n x1n plus a2 dot n x2n. So this part a1 and x1n, you can see that it is a1 n into x1n is basically y1n, and n into x2n is y2n. Okay. Hence the system is linear, because the output of this system to a linear combination of the two inputs x1 and x2n is actually equivalent to the sum of the weighted sum of the outputs taken individually. So this is a linear system, right? We'll be doing some more examples when we have the live demo session, but for the time being, this is what the property of linearity means.